be seated. At this venue, and that's primarily to convey the excitement of science to a broader public, because that is an essential mission of TIFR. This public lecture particularly is exciting and important because it's a collaboration between TIFR and LTPI, which is Lodha Theoretical Physics Institute, which is being officially founded this week in Mumbai as a part of a conference that's going to take place over the next couple of days, starting tomorrow. Lodha Theoretical Physics Institute is founded in turn by the Lodha Foundation, and as a result, this is a very beautiful experiment, a collaboration between institutions to bring eminent scientists to interact and answer questions, as we will see later on. So this kind of collaboration is fundamental to all scientific ventures, collaboration within the country and collaboration international. So this is just an example of this, and this is happening because both the Lodha Foundation and TIFR have this mission of doing cutting-edge research and also trying to communicate it to a broader audience. We are today very fortunate because we have some of the most eminent physicists, researchers with us today, and they have immense collective wisdom, which they're going to share throughout this evening. And in short, we are here to celebrate the magic of science, of the excitement that science brings to people who are practicing, and also to people who are thinking about becoming scientists, or public who are excited by science itself. So I'm really pleased to get this started. So at the outset, let me get the event started and invite some key people. Professor Anish Ghosh to the dais. He is representing Director of TIFR. Then I also invite Shri Ashish Kumar Singh. He's the Chief Mentor of the Lodha Foundation. I invite Professor Klaus von Klitzing to the dais as well. I invite Professor Bertrand Halperin to the dais as well. Professor Sankar Das Sarma. And Professor Jainendra Jain to the dais. Let me just say a few words about each one of them as they come to the dais. Professor Anish Ghosh is an accomplished mathematician, and he's the Dean of the School of Mathematics at TIFR. And he's representing the Director of TIFR, who had to be away for some prior meetings. Shri Ashish Kumar Singh is the Chief Mentor of the Lodha Foundation, whose leadership is helping shape a long-term vision for institution building and scientific excellence in India. Professor Klaus von Klitzing is well known. He's the 1985 Nobel laureate in physics and Director Emeritus of Max Planck Institute for Solid State Research, and his work has led to lots of exciting new fields, so you'll hear about it later in the public lecture. Professor Bertrand Halperin, Hollis Professor Emeritus of Harvard University. He's a pioneer in quantum Hall effect and low-dimensional quantum systems. Professor Sankar Das Sarma is a distinguished university professor and director of Condensed Matter Theory Center, University of Maryland. Professor Jainendra Jain is the founding director of the Lodha Theoretical Physics Institute, which, as I said, will be founded officially in the next couple of days as a part of a meeting. And he's also even Pew Professor of an Eberly Chair in Physics at Penn State University, a Wolf Prize awardee. He's internationally renowned for his pioneering contributions to condensed matter physics. So let's all welcome all of them. So it's indeed a great pleasure for TIFR and all of us to host this collaborative event. Let me get things started and invite Shri Ashish Kumar Singh. As I said, he is the chief mentor of the Lodha Foundation, and his leadership is driving this foundation, and the Lodha Theoretical Physics Institute is part of this leadership, which is sort of leading to this public lecture. So, Mr. Ashish Singh.
Thank you very much, Professor Ghosh. Distinguished Professor Klaus von Klitzing, Professor Bert MacDonald, Founding Director of the Lodha Theoretical Physics Institute, Professor Jainendra Jain, Professor Sen Sharma, Professor Ghosh, representing the Director of TIFR, respected faculty members of TIFR, eminent scientists, scholars, students, colleagues, ladies and gentlemen. I have never been more intimidated in my 36, 37 years of work life as much as I am today. I feel like I am a pigeon set amongst cats. It is my absolute privilege to welcome you all this evening on behalf of the Lodha Foundation. We have today with us one of the greatest experimental physicists of our time, Professor Klaus von Klitzing. His discovery of the quantized Hall effect in 1980 at the High Field Lab in Grenoble was extraordinary in elegance. It revealed that under certain conditions, electrical resistance appears in precise universal quantum steps. That one discovery changed not only condensed matter physics, it changed metrology. It deepened our understanding of the quantum structure of matter. It gave science a new standard of precision, the von Klitzing constant. 5 years after that observation came the Nobel Prize. 45 years on, the von Klitzing constant remains one of the most exact numbers human beings have ever extracted from nature. But I have no intention of preaching physics to physicists. I'm only trying to dwell upon, very briefly, on what such a discovery represents, because it carries a lesson far beyond the laboratory. Some discoveries are valuable because they solve an immediate problem. Others are valuable because they reveal that reality is more subtle and more astonishing than what we had imagined. The quantum Hall effect belongs to the second category. It arose from curiosity, from precision, and from the patience to take seriously what nature was revealing through an experiment. This, I would say, is the true spirit of fundamental science. At first sight, fundamental science appears distant from everyday life. It does not obey the impatience of the market or the electoral cycle. It often begins with a question that seems abstract. What is matter? What is symmetry? What is measurement? What is order? What is a constant of nature? And yet, history teaches us that humanity has been transformed by precisely such questions. This evening's lecture is therefore not merely a scientific event, it is a statement of institutional intent. The Lodha Theoretical Physics Institute, whose inauguration this lecture precedes, is being created in that spirit. Its purpose is to help build an institution of seriousness, of depth, and intellectual freedom. TIFR itself is one of the great symbols of that rich scientific inheritance. It was built on the conviction that a newly independent nation must seek intellectual sovereignty. That conviction is as relevant today as it was in the middle of the 20th century, because great nations are created by scholars, by mentors, by the presence of those who have themselves changed the grammar of a field. That is why Professor von Klitzing's presence amongst us today is so meaningful. He represents a tradition of science in which precision is philosophical. His scientific journey also reminds us that the smallest systems can reveal the largest truths. For our young students present here today, I would say this: it demands, think of science as a way of life. It demands rigor, it demands the acceptance of difficulty, but it offers something rare in return: the privilege of standing before reality without illusion and yet with wonder. I see today's event as a beginning of collaborations, a beginning of a culture in which the highest science is part of our shared imagination. We are grateful to Professor Klaus von Klitzing for being with us. We are grateful to everyone else, all the eminent scientists, to be with us. We are grateful to TIFR for its collaboration. And we are grateful to all of you, scientists, students, teachers, and citizens, for joining us in affirming that the life of the mind still matters. It is my absolute honor to be an attendee at Professor Klaus von Klitzing's public lecture. Thank you all.
Okay, thank you. Let me invite our Dean, Professor Anish Ghosh, to say a few words.
Thank you, Mandar. So, my name is Anish Ghosh. I'm the Dean of Mathematics at TIFR, and I'm here representing Professor Jairam Chengalur, Director at TIFR, who unfortunately could not be here today. So, at the outset, I'd like to say how delighted I am to see that the Bhabha Auditorium is full today for this wonderful lecture. Thank you all for coming. I know that your time is valuable and that you've had to travel a long distance to be here. So we really appreciate the fact that you have taken time out. And you've made a very good decision because today is going to be an outstanding event. We have amongst us the very brightest minds in the world and a Nobel laureate, Professor Klaus Klitzing, who's taken time out to visit us. We're very grateful for this. I'd like to say a few words about the Tata Institute of Fundamental Research. So research at TIFR covers a very diverse range of topics across the themes of physics, chemistry, biology, mathematics, and computer science. In many of these areas of research, we are one of the very few, if not the only, institution in India which undertakes this research and where such studies are carried out. So we regard it as part of our mission to have a vibrant outreach program and communicate to the public the excitement that we feel in conducting cutting-edge science. Our outreach program, TIFR's outreach program, is not just one of the oldest in the country, but also probably one of the largest and most varied. For example, at the location of our large radio telescope, the GMRT, we run annually what is probably one of the largest science day programs in the country. All of our centers in Mumbai, Hyderabad, Bangalore, and other places have very active outreach programs. Here in Mumbai, we have the classic and by now canonical Chai and Why series, which runs continuously on Sundays and has been running for more than a decade. Alternatively, at the Prithvi Theatre in Juhu and at Ruparel College. And of course, we have a long tradition of hosting public talks here at the Homi Bhabha Auditorium. I'd urge you to check our webpage and social media feeds for upcoming events on our campus. Today, we are truly delighted to host a very distinguished speaker, the Nobel laureate, Professor Klaus Klitzing. You will shortly hear a more formal introduction of the speaker, but I would like to take this opportunity to thank him on behalf of TIFR for accepting our invitation and coming here for this visit. This talk is a collaboration between TIFR and the Lodha Institute and will be followed by a panel discussion with a very distinguished panel. As all of us know, quantum technologies will be critical for any country going forward. So this is not only going to be a fascinating discussion, but also a very timely one. With that, I'll stop. Welcome again.
Okay, I request Dean Anish Ghosh to felicitate the distinguished visitors who are here for this public lecture. So, yeah, please. Okay, thank you, everyone. Thank you all for kindly coming onto the stage to get this started. I request all of you to sit down so that we can get the public lecture started in a couple of minutes. Yeah, it's fine. Thank you. Can you remove the chairs? Okay, just in case there are people who came later, please turn off your devices or mute your devices as we are getting ready to start the public lecture. I want to invite Professor Jainendra Jain to the stage to formally introduce our public lecture speaker, Professor Jainendra Jain.
So what a great audience. And what a fabulous evening of quantum physics we look forward to today. So after the public lecture, we'll have a rare opportunity to interact with some of the world's most brilliant minds. So that'll be Klaus von Klitzing, Bert Halperin, and Shankar Das Sharma. It's actually an honor for all of us to be here to listen to Professor Klaus von Klitzing deliver his public lecture. And it's my distinct honor, my distinct privilege to introduce him. So we heard already that Klaus received Nobel Prize for his discovery of the quantum Hall effect. And this is something that was discovered almost at the time when I started my PhD, and I still distinctly remember what reverberations it sent through the physics world. It was completely unexpected. And in time, we have seen that it has actually started a cascade of many new discoveries and many new subfields of physics. And it's something that's still growing, still has surprises, and it's still, I think its potential is still not fully known. So there are a lot of different new concepts that have arisen out of it. So it just, of course, Klaus has Nobel Prize, and many people have Nobel Prizes, but this is much more than a Nobel Prize in the sense that it's not often that discoveries have the kind of impact that Klaus von Klitzing's quantum Hall effect has had. So you can, of course, I could stand here and give you a list of all the different honors that Klaus has had, over the years, but you can find that on the internet. Let me tell you some things that you cannot find on the internet. So one thing that I have admired, or I admire extremely about Klaus, is his commitment to the field. So, Klaus is somebody who is heavily sought after by world leaders, presidents, kings. It's rare that somebody can have a dinner with the king and queen of Jordan in Petra. But I have found that for Klaus, and participating in physics conferences is always the highest priority. So just to give you an example, as was mentioned by Ashish Singh already, that we will have the 10th episode of this conference series called Emergent Phenomena in Quantum Hall Systems. So this is one of the flagship conferences in our field. And another flagship conference is called Electronic Properties of Two-Dimensional Systems. So there have been about 25 conferences in that series. Both of these conference series are biennial. And Klaus has participated in every single one of them. And I should also say, that the participation is not perfunctory. You know, he's there from beginning until the end. He's deeply engaged in all of the talks, and he finds time to talk to young people, young researchers, and it's actually extremely inspirational for all of us. You might notice that I may be the only person wearing a tie here, so let me tell you why I'm dressed like this. So over the 4 decades, or more than 4 decades that I have known Klaus, he has been very generous with gifts. So I have several gifts from him, which I proudly display in my office. And one of those gifts is this tie. So it's not an ordinary tie. It actually has his original description inscripted on it. You know, so I received this gift maybe 15 or 20 years ago, but until recently I had not an occasion worthy of this, worthy of wearing the tie. But last year, when Penn State organized some sort of celebration at the news of my Wolf Prize, I thought that was my time, so I put on this tie very proudly, and people actually loved it. So I sent Klaus a photograph of this tie, of my wearing this tie. He said, oh, so he has an amazing sense of humor, as you'll find out. So he said, oh, now you won't make a mistake in citing the correct equation for quantum Hall effect. So this means that no less than a Nobel laureate has given me a cheat sheet for an exam on quantum Hall effect. So anyway, it's an honor to have you here, Klaus, and you know, I'm sure you are not here to hear me, you are here to hear Klaus. So without further ado, please join me in giving a very, very warm welcome to Klaus.
Thank you. So, sound check, 1, 2, 3. Can you hear me? Oh, okay, that's important. Yes, today, Tuesday, 26th of May, 2026, there was a date 18 to 1930. No, this was another conference. So I had the choice today to go to different conferences, and I decided I go to the most important place, to Mumbai, and to give this public lecture here. So the other conference was in London at the Royal Society. And the title of the conference there is The Future of Science. So today you can ask the question, and this is not the full title, it was the title Future of Science with AI. Everything fears about jobs, for example. Do we have in the future AI scientists? Do they get the Nobel Prize in the future? So this is a question. I'm invited to many conferences to speak about the future of science and AI. Now, I decided the more important conference is in Mumbai, because we have here the situation that we have this conference and to meet people, to interact with people. So I prefer to come here, and we have 2 important questions. So I asked artificial intelligence about AI scientists. Will they replace scientists? And the answer from AI was, AI is conservative. It extrapolates from known patterns and it rarely proposes radically new theories on its own. And many breakthroughs required conceptual leaps beyond existing data patterns. And I will demonstrate today, in my case, I think AI had no chance to find the quantum Hall effect. Because the pattern was against it. AI is best seen as a tool, it's not a scientist. And excellent in analyzing data and spotting patterns, but it's weak at deep understanding, creativity, and judgment. So in the summary was, the most effective scientific progress today comes from human-AI collaboration, where AI accelerates computing and humans guide the interpretation and the theory. And this is my conclusion, and I am fighting, even today, I'm an advocate for basic research conducted by humans, and this is the reason that I'm here. And tomorrow we will open a new institute. I think this is such a fantastic situation that we believe in human intelligence. Now we have special celebration. We have here two. One is the theoretical physics, and the other one is this conference, Emergent Phenomena in Quantum Hall System. And last month I looked at the newspaper here in India, and there was an announcement. The Lodha Physics Institute in Mumbai will be paradise of theoretical physicists, and Jananda Jain will be the founding director. And pure research environment is a goal, like in my institute at the Max Planck Institute. And it was called that we have a paradise for theoretical physicists, and it will be the mecca for people coming to this place, an international meeting point. And I have such a situation at my home institution. This is my mecca of my research activities, the Max Planck Institute for Solid-State Research in Germany. And this is our institute, and if you visit us, you will find a sign, the von Klitzing pass to come to this institute. This is the entrance, and I found a book called The Jain Pass. But I discovered it should be not the pass, perhaps the elevator, because this will be the institute at present at the top floors. And we will visit it tomorrow, perhaps, to see this new institute. But in the future, if it expands, and you know, Lodha companies, they can build fantastic buildings. There will be a new paradise for science somewhere else, perhaps in the future, if you expand it. And okay, perhaps the new LTPI will expand to a new Jain temple. Yeah, I visited this temple. It's really impressive. But I'm not sure that it's the best place for scientists there, because I found the rules to enter the temple and to behave correctly at the temple. And it says, okay, it's not allowed to have liquor and other drinks, and transistors are not allowed. And today I will demonstrate without transistor and without a glass of wine, which facilitates the interaction between people. I had no chance to win the Nobel Prize. So this was an announcement in the press, the paradise, and I saw that the Lodha company started in 1980. It's correct, yes, 1980? This was exactly the time when I discovered the quantum Hall effect. So I will focus today a little bit on this quantum phenomenon, on the quantum Hall effect. I will speak in general terms about this effect. Now, I asked AI or ChatGPT, what do you think about quantum Hall effect? And how important is the quantum Hall effect? And the answer was the following: the quantum Hall effect is extremely important. Both in fundamental physics and real-world technology, its importance is so high that it's considered one of the landmark discoveries of modern condensed matter physics. And the bottom line answer was, So the ChatGPT is doing like a human. If I had to rank it for physics, one of the most important discoveries in the last 50 years, for measurement science, absolutely essential, and for future quantum technology, highly influential. So that's the status, the statement about the importance of quantum Hall effect. And you heard already about this conference series, the emergent phenomena of quantum Hall physics, and I show you the first advertisement of this conference 20 years ago. This is the EPQRS, normally the international meeting of people working in this field. And we had already the introduction of famous scientists in this world. So originally also MacDonald, he had trouble with the visa, so he's not here, he will come tomorrow perhaps. So Bert Halperin, Shankar Sharma, and MacDonald, these are some heroes in this field. They are theoreticians, I'm experimentalist, therefore I will focus today on experiments. And this field of quantum Hall physics has so many different topics. If you look at the announcement of the conference, which will start tomorrow, you will see all these words: integer, fractional quantum Hall effect, fractional charge, Chern numbers, composite fermions, abelian, non-abelian, anyons, chiral Luttinger liquid. So I can read the whole list. You find it in the internet. And if you want to understand something of this, you have to come to the conference. I will not cover this, but it's a very, very broad field with many, many different aspects. Now, I will go back really to the discovery and will make some historical remarks. So the historical remarks about the quantum Hall effect discovered in 1980, and I can fix the exact time when I saw an unexpected result. As an experimentalist, you see the truth already in nature. And at this night, it was 2 o'clock in the morning in Grenoble, and this is a famous picture. Okay, this was done 5 years after the discovery, because when I got the Nobel Prize, then the journalists wanted to have a picture. And so I went back really to the place, but this is the real situation. Only one thing is wrong in this picture. I have never a white coat as a scientist, but the journalist said, okay, as a professor and doctor, you need a white coat. So this is wrong, but all the other things, and you see, it is Grenoble in France. You see red wine, Côte d'Iron, some baguette, some cheese. This is typical for French culture. And alcohol is forbidden in the laboratory, like in the Jain temple. But in France, it's like water. Yes? So therefore, we had always at midnight, because I worked at night, because I need a lot of power, and the power was cheaper at night, so I started in the evening until the morning of 6. Therefore, the discovery was close to 2 o'clock in the morning when I saw something unexpected in the experiment, and I will show you how this experiment looked like. So when it was published that I discovered something at 2 o'clock in the morning, there was automatically other people said, okay, Grenoble, 2 o'clock in the morning at this day, I had not a chance not to see something special because the sun, the moon, the stars were in a special configuration, and these pictures were published with the time, and they discovered it was not 2 o'clock in the morning, it was 5 minutes past 2, because then the sun, the moon, the star had a very special constellation. I show this sometimes, mainly in Asian countries, to convince you that you should not believe in astrology. So, okay, and this discovery then already 5 years later gave me this Nobel Prize. I have here this prize here. Oh, and I know I'm just invited because of this prize, otherwise. And my story will be also, you should never work just for the Nobel Prize. The probability is small. You have to be lucky that you find at a special time, special environment, something new. So you should be happy if you see something unexpected. Now, my first publication was in 1980 about the quantum Hall effect, and this started the field of the quantum Hall effect. You see, okay, we'll go back. You see here, quantized Hall resistance was mentioned at the publication 11th of August 1980. And I had already, before this date, first publication connections to India. I will show you a letter I received here from the National Physics Laboratory. The director wrote to me, and you see the date, 8th of August 1980, 3 days before the paper was published. Because I attended a conference and I gave a post-deadline paper at a conference before I published my result. And I also want to encourage people doing research to interact with others even if you have not published it. Because if you can convince other people that you have done good work, I think they will accept that you have done to keep the priority. Today, there's always a fear that somebody will steal your ideas. But there are so many open questions in science. And I always like to interact with people. So I spoke at a conference. And at this conference, in this post-deadline paper where I presented my results, the people were enthusiastic about the results. And from this time, I had a lot of connection to people in national laboratories because they can apply this effect immediately. So it was mentioned that during this small conference where I gave a post-deadline paper, we are very much excited on your paper entitled New Method for the Determination of Some Constant based on the quantum Hall resistance in MOSFETs. And from this moment, I started already cooperation with India. So I accepted people from the National Physics Laboratory here. They stayed in my lab. I sent the samples that they could start the experiments. And at my last visit, I visited the laboratory at the NPL in New Delhi. So this is a simple experiment. You see, not too much. There is some cryostat for low temperatures. There is some rack for electronics. That's all for the quantum Hall effect. This is a very simple experiment. Not really a big instrument is necessary to do this research. And our students have to do this experiment for their physics study. So here in India, you have special laboratories, quantum resistance metrology and two-dimensional physics. And you see they can now calibrate resistance in the range from 1 ohm to 1 meg ohm with very high precision. This is one of the applications of my discovery. And just recently, I was elected as an honorary member, you see here, honorary member of the Metrology Society of India, because this application is so important. And my talk today will be really quantum science. Quantum physics is very, very important field, a worldwide activity. So I have chosen the title, Why Quantum Research Matters from Curiosity to Real-World Impact, because the quantum Hall effect was driven by basic science, and suddenly, after 40 years, it had very, very important impact on practical application. And I will tell you a little bit this story. And this quantum physics, everywhere in the world, we have today some special programs about quantum science. Here in India, I found a special program until 2031. You have a special program on science in quantum science technology. So last year, we had a worldwide activity about quantum science and technology. In all countries, there were activities in this field to demonstrate how important it is. In former times, there were other fields, for example, nanoscience. Nanoscience is more or less identical with quantum physics, with old-fashioned quantum physics. And for the physicists today working in modern physics, they are always dealing with quantum physics. So there's nothing new. Sometimes we need a new word for our research. And I have done all my time something in semiconductor quantum structures, and therefore quantum science is our daily life. Now, for this world year of quantum science technology, we had a history wall of quantum physics. And here you see the time of the start of quantum physics around 1900. And the most important results or the starting point is a constant called H, the symbol of quantum world. That's the Planck constant. And this was the starting point of quantum theory. And the simple question at this time was, what is the radiation coming out of a hot heater of a so-called black body radiator? And it was known that the spectrum depends only on the temperature. If you have a high temperature, then the color changes, the spectrum changes. It starts with red if you have low temperatures and going to white if you have higher temperatures. And this spectrum was known from the experimental side, and Max Planck, a theoretician, tried to explain the spectrum. So this is a spectrum. Here is the wavelength, and here is the color of our sensitivity of our eye. This is a short wavelength, the high energies is blue. On this side, we have also some radiation which is not visible, X-rays, for example. Here is the red, far red radio waves are in this range. And this spectrum is shown here for different temperatures. This was known very well, and Max Planck, as a theoretician, he developed an equation to explain this spectrum. This was a breakthrough, and he added in his equation two constants, which is called today the Planck constant and the Boltzmann constant. So Max Planck introduced these new constants to explain the spectrum of some heater. And the very first publication was in 1900 about the start of this quantum theory to explain the equation for this black body radiation. And if you look at this original paper, unfortunately in German, then the last section of the paper is natural units. So Max Planck, he was more fascinated by the fundamental constant, the Planck constant and the Boltzmann constant, than in quantum theory, because he didn't believe that this quantum theory, which means finally that light consists of energy packages. So it's not just a wave, it's really, yes, the quantized energy plays an important role, but Max Planck didn't believe that this has something to do with reality. Today we know so-called photons is our standard picture of the finite energy of electromagnetic waves. And he was so fascinated by fundamental constant and made this statement in the publication. So if you look at the original publication from 1900, the translation is, with the help of fundamental constants, we have the possibility of establishing units of length, time, mass, temperature, which necessarily retains a significance for all cultures, even unearthly and non-human ones. So really, he was so fascinated that these constants are present everywhere in the universe. So, and he introduced then Planck units for these quantized, for these units. So he introduced the Planck constant and the Boltzmann constant, and the velocity of light was known already, and the gravitational constant, the force between two masses. So he combined these fundamental constants and then could produce Planck length, Planck mass, Planck time, Planck temperature. So this is just a combination of these fundamental constants. So these are natural units. So it was a fantastic idea of a theoretician, but as an experimentalist, you have to make the statement not useful for practical application. Because if you look at 10 to minus 33 centimeter, in our daily life, we are not dealing with such length scale, or with the other quantities. 10 to minus 43 seconds is not the time we are using. I'm very happy that Max Planck didn't include another constant in his treatment, the elementary charge. It was already known around this time that we have quantized charges, the electron charge, because then he could also combine this with the Planck constant E square, and this is 25,812 ohms. And this is exactly the quantum Hall effect. So the quantum Hall effect is the only one which is in a scale which is useful in our daily life. 25 kilo ohm is the best resistor to do measurements. It's just in the middle between an insulator and a very good conductor. So this is fantastic that you have a quantity which is in a range which is useful for our daily life. And this was finally my discovery, the quantum Hall effect. And this quantum Hall effect added a new facet to the quantum world. And last year, in Nature Materials, there was a publication, lots of different Hall effects. And there was this picture which starts with Edwin Hall. Edwin Hall lived from 1855 to 1938, and he discovered the classical Hall effect. The classical Hall effect, you have a conductor, a current is flowing through this conductor, you apply a magnetic field, and then the blue voltage, the Hall voltage, appears if you apply magnetic field. So this voltage increases with magnetic field, it increases with the current through the device. This was the discovery in 1879 by Edwin Hall. And now in this Nature article, it was mentioned here that a remarkable milestone was the discovery of the integer quantum Hall effect, marks the entrance of the Hall effect into the quantum territory. And we have today many, many Hall effects. So in 1879, the classical Hall effect, my discovery, 1980, the quantum Hall effect, then 82, the fractional quantum Hall effect, the quantum spin Hall effect, quantum value Hall effect, quantum anomalous Hall effect, fractional quantum anomalous Hall effect. These are topics which we will partly also discuss at the conference and the rest of this week. Now, if you go back to the quantum history wall, this decade between 1980 and 1990 was really very important part, not only because of the quantum Hall effect. If you see in the history wall, this is the official history wall of discoveries in this decade, you see high temperature superconductors, 1986. Then here, aspects entanglement. So this is today very important aspect of quantum theory. Or here, very important experiment, wave and particle nature simultaneously. This is a picture where these white dots are electrons falling on a detector, and you accumulate these electrons, and you see some interference pattern after some time. So you have to solve this problem that electrons can have a particle picture and can have also a wave picture generated some interference. And these are all measurements in this decade, but I have to concentrate on the quantum Hall effect. And this is a classical Hall effect, a straight line, and these steps, this is a quantized Hall resistance. And Janandra showed already the tie. The tie is a copy of my original notes today in a museum in Germany. These were really my notes in my workbook, where I had here the design of the sample, and here the important equation which Janandra will always remain in exams. So the Hall voltage, and here is the current, and the proportional constant is this fundamental constant. This was a surprise that really with macroscopic voltage, macroscopic current, you can measure a resistance which depends on constants of nature, which has a value of 25,812.807 ohms. And this was called then the von Klitzing constant. So the experiment is really very simple. So you have a black box, put a current through this box, and inside is a quantum Hall device, a material-independent resistor. You measure this voltage, and this blue voltage divided by the red current gives you the value Planck constant divided by elementary charge squared. My research was not to discover this effect. I was interested in understanding microscopic picture of the most important device in microelectronics, a field effect transistor. So this was the device where I discovered the quantum Hall effect. This is a silicon field effect transistor, but it has more contacts than normally in our devices, because you can measure here also the Hall voltage. And its basic research on this most important device in microelectronics led to the unexpected discovery of the quantized Hall effect. I was interested to understand microscopically the motion of electrons in such a device. If a current is flowing, how can you make the device faster? How can you make it smaller? This is one of the devices to apply it for modern microelectronics. So my field of research was how to understand the movement of electrons in MOSFETs for smaller and faster devices. And the experiment was really simple. The current in this device, then the Hall voltage perpendicular to this device. And I will show you how an experimentalist discovers something unexpected. And I will show you a sketch about our experiment at this time. At this time, we had no computer to accumulate data. We used the so-called XY recorder, so you have a sheet of paper and a pen is moving on it. Here is something which is proportional to magnetic field. In the other direction, I measured the Hall voltage, and the classical Hall effect should be such a straight line. So this is a normal experiment to get some information about the number of electrons active in your device. And the experiment always shows you some deviations. And as a good scientist, you know, okay, this has some physics, there is some temperature change, some noise, some vibration, you have some deviations from this ideal curve. But if you aren't interested in the slope, it doesn't matter. But I saw something here close to the upper limit of the XY recorder. This was 25 centimeters. I used 1 microamps normally. This is 25 kilo ohms, the upper limit of the XY recorder. And there was some noise here, unexpected, but I remembered this noise I saw also for another sample from another supplier, and it was a reproducible plateau close to the upper boundary of the sheet, up at the 25 centimeters, 25 kilo ohm. And this peak today is the quantized Hall effect, this small deviation from the straight line. And today we can optimize this. This is already 10 years ago published. Here is this Hall effect, the red curve as a function of magnetic field. You see the red curve, and then it stays constant for a long, long magnetic field range. And this is a value, the quantized value, the Hall voltage divided by the current has here a fantastic constant value. And there are two ingredients, quantum physics ingredients, to observe this. Two quantum phenomena necessary for observing the quantum Hall effect. We need so-called discrete energies. We need a two-dimensional electron system, so that electrons can flow only in one plane, and we need a strong magnetic field. So these are the two ingredients to see this. And our students today using graphene, because graphene is such an ideal two-dimensional system, there's only one layer of atoms, and you can make contacts here, can put a current through such a graphene layer, just applying magnetic field and measuring the Hall voltage, and then you have this wonderful, nice result that you have this fundamental resistance. Now, I will show you one picture about the physics. I will not go into the theory of the quantum Hall effect, but one useful picture is the following. If the red area is a device, and in strong magnetic fields, the electrons, like in atomic physics, they can make a closed orbit. And so this is like a hydrogen atom, but we have not a positive charge in the center, just the magnetic field turns the electron on closed orbit. And this is the definition of high magnetic fields, that you can have these closed orbits without scattering, without disturbing. And from quantum physics, one important statement is that each this orbit needs a certain area. And the area for one cyclic orbit, this is quantum physics, is this value, which with stronger magnetic fields, the orbit becomes smaller, therefore the area is smaller. So the area of so-called one flux quantum in real space is occupied by one electron. And if you add another electron, it has occupied another area. And if you have completely filled sample space, this is the quantum Hall effect. The quantum Hall effect is closely packed electron orbits, and because it's an incompressible state, because you cannot add here one electron, you have to go to higher energies. So this is the simplest picture, but it's always dangerous to make pictures in quantum physics. Also, the picture we learn, the Bohr orbit, that an electron is moving around the nucleus, is a nice picture, can explain many things, but strictly in quantum physics is not the correct picture. But the quantum Hall effect works better than expected. So I published a value for this resistor, 25,812.68 ohms, plus minus 8 for the last digit. This was my uncertainty. And immediately other groups here in France, Germany, United States, Canada, they repeated the experiments and they had much better equipment, so they measured these values. And you see all of them within the uncertainty, that's the error bar in the experiment, they found the same value. And the breakthrough came through measurements of the National Bureau of Standards in the United States, because immediately after discovery, they measured the official ohm in the United States. By law, the official ohm in the United States is the ohm kept at the National Bureau of Standards, or today NIST, in the United States. So this was the official ohm in the United States. And they compared this official ohm against this new type of resistor. So for 5 years, they measured the difference in the resistor between this ohm and the quantum Hall ohm. And they found experimentally such a curve. So as a function of time, the deviation between the two changed. So you can say, okay, the quantum Hall effect changes with time, but they used 3 different devices and they are on the same line. So the conclusion was, okay, the quantum Hall effect is more stable than any wire resistor, because the wire resistor, there's some strain inside, there's some absorption of impurities, so there are changes in the wire resistor, and the quantum Hall effect works much better than any wire resistors. And all metrology institutes in the world, they immediately compared their ohm against this. Some had a positive slope this time, some negative slope. So everyone agreed, okay, it's wonderful to use the new quantum Hall effect to have the same value everywhere in the world. And so in 1988 already, it was defined by the so-called Comité International pour la Mesure. They recommended that 25,812.807 ohms exactly. So this was the best value of all the measurements all over the world, adopted as a conventional value, denoted R for resistance, K for Klitzing, and 90 for 1990, because they started in 1990, and that this value should be used from 1st January of 1990, so that all countries in the world have the same basis for calibrating electrical resistors. So this was the decision, and they introduced so-called conventional value of the von Klitzing constant. This was some agreement that this was the best value, and everyone should use this fixed value for this new quantum effect. And the same, I will not discuss it in detail, has been done for the Josephson effect. This is an effect in superconductivity where you can produce a voltage based on the so-called Josephson effect, and also a fundamental constant 2E over H plays an important role, and they fixed also this value. So 2 electrical units were fixed so that all over the world we had this ohm with index 90 and the voltage with the index 90. And we had these stable quantum units, but outside our official system of units. I will come back to this international system of units because we have some worldwide agreement about our measurement system. And this definition was used between 1990 and 2019. And I will focus at the end of my talk on the year of 2019, where they changed our international system of units so that these quantum physics is integrated in our official system of units. So I was very lucky to have this constant, and it's not often that a physicist has their own constant. You know, the Newton constant or Loschmidt or Faraday constant, Planck constant. And here at the end, you'll find 2 constants, and most of them died already a long time ago. We are the only living constants, yes? So quantum electricity gives you their own constants, so Brian Josephson and I, we are the only constants. Now, one has now compared really the quantum Hall effect for different materials. It was discovered on silicon field effect transistors. Gallium arsenide is still the gold standard because you have better quality of the devices. And there was a comparison, silicon against gallium arsenide, and they found the same value with this uncertainty. Different devices from different wafers, or graphene against gallium arsenide, different type of graphene, the so-called fractional quantum Hall effect, or the quantum anomalous Hall. So many quantum effects are compared, and the final result is that now differences at the level of 1 part of 10 to 10. So we have a universal resistor, which is the same for different materials if we measure this. So the quantum Hall effect really opens this new research field, not only in metrology, and it will show you some directions also of application of the quantum Hall effect. And today it's modern to show citations of the original work. So this was in 1980 when I published the first Fusref paper, and this is a citation as a function of the years. And you see there's a strong increase at the very beginning up to the peak, and the peak was my Nobel Prize, because then all the people that wanted to join this effect, to explain this theoretically or to do some extra work, they published something, and after I got the prize, they relaxed it a little bit. But then you see a nice plateau. Here is a plateau typical for quantum Hall physics, 70 citations per year. And then around 2006, this is the citation rate. So there's a strong increase by a factor of 5. And our international conference meeting started around this time. You see, there's a big drive. And there's even a publication just discussing the citation. Why suddenly an old paper has a revival in a certain field. And I can show you this publication. This is a publication, especially the Journal for Scientometric. How can revivals of scientific publication be explained using this analysis, a case study of the quantum Hall effect? And you can look at this publication, they analyze the citation and the impact. So a dark blue is the old-fashioned quantum Hall effect, the two-dimensional electron system, integer quantum Hall effect, tunneling, gallium arsenide, even the graphene started. So this is the old, because the color is the age of the citation. And then you see yellow, these are more during the last 5 years. And you see here the subtopic topological insulator. This is really a fantastic new field which is connected to the quantum Hall effect. And sometimes you will find quantum Hall effect, the first topological insulator. I never thought about topological insulator when I made measurements of the Hall effect. But the topological insulator is this really fantastic material. This is just not a correct picture, but it demonstrates the electrical behavior. If you have a porcelain plate with a gold boundary, then you know this is an insulator. At the boundary, you have here a conductor. But we have materials, one material, which automatically always at the boundary is conductive, and the inside is an insulator. So this is really a new class of material, and this is a fantastic new field. And since the quantum Hall effect has such a property that it looks like an insulator, and at the boundary a conductor, is called the mother of topological insulator. And these two-dimensional topological insulator have very, very fascinating properties. And last year I saw in Physics Today this picture, for example. This is the yellow electrons, and the exchange of electrons is illustrated in this picture. You know, electrons are identical everywhere in the world. So this electron and this electron, if you look at it, they are identical. But if you exchange them in this system, quantum physics says that the wave function of the system changes the sign from plus to minus. This is one property. But if you change the twice, so two exchange first and then going back, then you have the starting station. This is the general picture. But in two-dimensional system, we have something very, very special, and this is one of the hottest topics today in this field, because I have stolen this picture from Charlie Marcus. In two-dimensional system, if you make a closed orbit, you have the possibility to have inside the orbit something mysterious or not. In 3 dimensions, you can avoid such a singularity, but in 2-dimensional system, there's a difference if you go around this object, which changes the phase if you do this circle. This is really a new field, and normally in physics we speak about fermions or bosons, but we have so anyons. We have a new quality of physics which is just in 2-dimensional systems. Therefore, these 2-dimensional systems are so fascinating. And if you look at the homepage of this conference here, you see such logo where you have these pictures of interacting so-called quasi-particles, and this is really some special field. And this is important for topological quantum computing. This is one of the hot topics in our field, a contribution to quantum physics for quantum computer, but it will take a long time. I will not go into this direction. I will just focus on this methodology because this was the first surprise when I discovered the quantum Hall effect, this fundamental value of a resistor. And really, this discovery led to a new international system of units. Our international system of units, I will just explain it, was changed in 2019. And I will just tell you a little bit about this application of the quantum Hall effect. The quantum Hall resistance revolutionized 40 years after the discovery our international system of units. Before I showed you, it was just used as a conventional value to reproduce some resistor. But in 2019, we included the quantum Hall effect in our international system of units. And you should know, and this is important, that everything what you can measure can be traced back to 7 base units: the kilogram, meter, second, ampere, Kelvin, mole, and candela. These are the 7 base units, and everything in astrophysics, in high energy physics, in biology, chemistry, can be traced back to these base units, and therefore these base units should be stable and everywhere the same in the world. So this is the idea of our international system of units, that we have accurate values for these base units. And in 2019, we changed base units, and there was an extra stamp here in Korea where we have these 7 units, the kilogram, meter, second, ampere, and so on. And the mole, the Kelvin, the kilogram, the ampere, they changed, and one reason was the discovery of the quantum Hall effect. And on May 20th of May 2019, all countries changed their laws to accept a new definition of these base units. And this is very important. And the situation 10 years ago was the following. We have these 7 base units. And the second, the atomic clock, was the first one where some atomic properties were used. So the atomic clock works very, very well. We have the cesium clock still since 1967. But the meter is not anymore the meter of a standard. At the time around 1980, when we tried to measure the velocity of light with very high accuracy, it was found that the meter was not accurate enough to measure the velocity of light. And at this time, there was a decision to fix the value of this fundamental constant, and the official definition of the meter is defined by taking the fixed numerical value of the speed of light in vacuum. This value was fixed when expressed in units of meter per second. So that was the first time that a fundamental constant was fixed to have a new definition of one of the base units in our system. And now the question arises, how can I integrate the quantized Hall effect? Officially, in this old system, 1 ohm is 1 kilogram meter squared second to minus 3 ampere minus 2, because we have identity between electrical and mechanical energies, and we have Ohm's law. So if you use well-known equations, you know that the ohm is related to these base units. So therefore, in our international system of units in the old time, you have to relate this to this definition of our base units. But how can the quantum Hall effect be integrated into our international system of units? So you have to give up. You cannot just say, okay, we have this resistance with this value. we have to give up something in the old system. And the solution was the following: to give up the kilogram and the ampere, the old definitions. And anyway, it was shown that the kilogram prototype, the piece of metal in Paris, was not stable, and therefore everyone was happy to replace also the kilogram and the definition of the ampere. And these new definitions connect the ampere to the elementary charge and the kilogram to the Planck constant. And if you fix the Planck constant elementary charge, then automatically h over e squared is a fixed number. So this was the idea to replace then these system, these quantities, by a new definition to fix values of fundamental constant. But you need some experiments to realize them, and fortunately, there are some experiments where you can relate the Planck constant directly to the kilogram and also the elementary charge to the ampere. And the most important conference in my life was a conference held in Paris in 2018 to discuss the change of our international system of units. And I have here a picture from the New York Times of this meeting of the International Committee of Weights and Measure. So this is an organization since 1875, every 4 to 6 years, different countries meet to find out the best measurement system which is acceptable for all countries in the world. And in the New York Times was a report of this conference, and I was there, gave a talk, and it said, this publication, New York Times, representatives of the Meter Convention voted unanimously to redefine our basic units of measurement, the kilogram, the mole, the Kelvin, and the ampere. And among them was Klaus von Klitzing, front row, taking a picture. Normally I don't take a picture, but I should do this here. You see, I'm here taking a picture because this was really an emotional conference. There was the people, the delegates from all countries stand up applauding for a new international system of units, fixed values for natural constants. And really, this was such an excitement. You see here the audience, the representatives, and the excitement was so high because all countries agreed. In Europe, we are happy that Turkey and Hungary at this time, because normally they prefer to vote no because they want to have more money from the European Union, they voted yes. And also American, the Russian, the Chinese, all of them agreed. So this was an international conference where all countries agreed to change our international system of units. And I think this was a wonderful example that science has no political borders. So this is a scientific truth, and really this quantum metrology united all countries. And I cannot believe that we will see such an agreement between all countries in the near future. So this was really a conference where all countries agreed, and I was happy to convince them to see the positive development if we use fundamental constant for a new definition. And if you didn't understand anything, I will just summarize again our new international system of units, because if you have to teach a physics class, normally at some level you introduce the base units, and you should avoid the explanation that the kilogram is a piece of metal. This was the old definition. Since the French Revolution, more or less, they decided to use this prototype kilogram, which is more or less 1 liter of water. But this is not the definition today of a kilogram, this prototype. The definition is a fixed value of the Planck constant. This is a value which will never change in the future. We have fixed this value, and from measurements starting with this value, we can realize the kilogram, and we'll show you this later. The same for the temperature. We learned temperature scale. We have a triple point of water, that we have melting of water, or the so-called triple point close to 0 centigrades. This was a fixed value, and the absolute zero fixed the temperature scale. This is not the official definition of the temperature scale today. We fix the value of the Boltzmann constant. This is a fixed value, and then we can think about many different experiments to produce our temperature scale. And the same for the electrical current. The original definition of the electrical current, if you have two wires and the current flows through this wire, then you have a certain force. So this was the official definition of 1 ampere. And this is not the case anymore. The ampere is fixed by a fixed value of the elementary charge, because the time from atomic clock is very well known, and the charge per second is the current. So this fixed value of the elementary charge defines the base units ampere. And the same mole, when I studied, I learned that the mole has something to do with 12 grams of carbon isotope. This is not the case anymore. We have fixed the value, amount of substance. This is a fixed value for the so-called Avogadro constant. And I will, at the end of my talk, just mention a little bit about the kilogram, because kilogram is the most famous base unit. And you should remember from this talk that we have a new kilogram based on the Planck constant, and the Planck constant is the starting point of quantum physics. And therefore, it was not easy to introduce this, because all the organizations which are using the kilogram said, we don't believe that you can use quantum physics to calibrate the kilogram. But these are the experiments. I visited all of these institutions in the world, and you can have a way from a fixed value of the Planck constant to a new kilogram. And one way is the so-called Kibble balance. These are balances shown in this picture. I have here one balance in operation from NIST in the United States. So this is a balance. On one side, you have some force on the other side. And even there are some moving things to calibrate the whole system. So it's not an easy experiment, but with this experiment, you can start from a fixed value of the Planck constant, and you can realize a kilogram with 8 digits accuracy. And the simple picture of this, I have here a Lego balance. So you have a balance where you have two forces on the both sides. So one side here is a kilogram, and you have some mechanical force due to the kilogram. And the other side, you compensate this with electrical force. And for the electrical force, you need the quantum standards like the quantum Hall effect. There's like an electromotor current flowing through a coil. So the electrical force, electric current, magnetic field, calibrated with quantum standard. And if you analyze such an experiment, you have a one-to-one relation between the Planck constant and the mass. In former time, this experiment was used to go from a kilogram in Paris to a good value of the Planck constant. Now we're going other direction. We fix this value, and everyone who can build such an equipment can produce his own kilogram. And a typical laboratory looks like this. Here is the quantum Hall devices, and on the left side, you need also the Josephson effect to have a calibrated voltage. So these two quantum effects are used to calibrate finally the experiment for a realization of a kilogram. And in Germany, we have even a prototype for industry for this so-called Planck balance, because the Planck constant is the basis. So here, this balance is not compensated by other mass, it's compensated by some electrical force. So you can use such a device to have a kilogram based on the Planck constant. And our new international system is shown here with the stars are these new bases, new values for this constant. And the Planck constant has these fixed values, and the elementary charge has other value, and therefore you can calculate the constant HRV squared, and it has really these numbers, the first 1,000 digits, to calculate this from the fixed value of H and E. And you see the value, this was the original conventional value, but we have much more digits in this ohm. And now you can still ask the question, are there corrections to this value? We just showed experimentally that with 10 digits, different materials have different, have the same result, but are there some special corrections, quantum electrodynamics or gravitational fields? Do they play a role? And there are publications that the gravitational potential is not important. In atomic clocks, we know that the gravitational field plays a role for atomic clocks, but not in the quantum Hall effect. But there's still some discussion of whether we have other corrections. But very fundamental question is still, are fundamental constant really constant? So this is really a question which is allowed. Do we know that the fundamental constant were always the same, even at the Big Bang? What were fundamental constants? And there's one constant which is very important, the fine structure constant, alpha. The fine structure constant is a combination of Planck constant, elementary charge, velocity of light. And one can measure very accurately today the change of the fine structure constant per year. And this change is smaller than 10 to minus 18 per year. So we know that with 18 digits, we have no change in of the fundamental constant with time. So the constants of nature are the most stable basis for a universal system of units for all times, for all people. This was the idea during the French Revolution to introduce the prototypes. And we have now this logo. On the outside, we have the old-fashioned definition of the base units, and on the inner part, the values of fundamental constants. So this is the idea, and 2018 was really a quantum revolution in metrology. But now we have other revolutions. I just looked at a book which appeared for the World Year of Quantum Science Technology. 2025, Quantum 2.0 is a modern topic, and it says that we have really a quantum revolution now in this field, which has something to do with entanglement, which is important for quantum computers. And so therefore my final statement is quantum science technology is a fantastic field for basic research and international cooperation, and good luck for the new institute. I should show at least one picture which is related to the founding director of this new institute, the so-called composite fermion. I have here just a picture which has so many aspects in different fields, and the discovery of Jananda Jain is really a higher level of quantum Hall physics. I will not cover this here, but this picture of this composite fermion is really a new picture. I compare this with so-called effective mass in semiconductor physics. We are using complicated interaction of electrons moving in a device by replacing the mass of an electron by some effective mass. And here, Janandra has introduced a new fermion which covers all these interactions which are complicated in a simple equation. And this opened really a new field, and thank you for your attention. And if there are discussions, we'll have a panel also. That quantum computation as a hype problem. Perhaps we can continue with this discussion because quantum computation is today everywhere in the world, one of the focus, and the driving force was security problems. And unfortunately, this field damaged a little bit the international cooperation because there's the argument that in the United States for national security, you should not cooperate with other people if you're working in this field. And this is a damage to science in general. And I want to slow down this hype because we have secure methods today, and we should not fear the danger. We should use it, the possibilities of the fantastic science behind it. But this is really a problem, and since 2019 or so, there is worldwide programs, and the competition or the fear, and mainly China against the United States, this fear drives this field, and this is unhealthy for science. But this is the other question. Perhaps Shankar can also contribute to this if he discusses. Thank you.
Okay, thank you, Klaus, for an amazing lecture as always. We are going to have some question answer. You're part of that panel, so I'll have questions and maybe one or two questions at the end from the audience. Thank you very much for an exciting lecture. Jainendra, do you want to say a few words? And we're going to set up for the... Yeah, okay. So we'll just set up the chairs for the panel questions. More people onto the dais to join Professor von Klitzing. I invite Shankar Das Sarma, Professor Shankar Das Sarma, and Professor Bert Halperin. Please join us on the stage. Have a seat.
You talk. This is the one I never heard before.
Don't attend my talks.
Okay. After that very invigorating lecture, exciting lecture, we have some panelists who are eminent researchers in this theoretical physics as well as experimental physics. And over the last month and a half, there was a web page which sort of collated interesting questions from people that could be asked at this occasion. But just to get started, maybe I'll ask a question to all of you one by one to get started. What do you think is the role of quantum science or research in quantum science for a developing country? If you could, country like India, if you could say a few words, and then we go to sort of the main questions that we have received. So maybe Shankar, you can start. What is the role of fundamental quantum science in a developing country?
You know, this is a difficult question because this has a scientific, it has a scientific aspect, but it also is a political aspect because of the word developing, right? So I think the science, of course, is universal, which is what Klaus emphasized so eloquently. So the scientific part, we are all the same. You know, it should be done as actively and as vigorously in India as it is being done in the United States. So, you know, to be very specific, in theoretical parts of quantum science, there is a difference because with theories you do not need equipment, and develop the difference is very little. But when it comes to experiment, there is an issue because to do the best experiments, you need the best equipment, and that's very expensive. And then each society has to make its own judgment of, you know, resources are limited, and whether you want to put huge amount of resources in quantum science, limited. I mean, I can talk about it all day. I have thought about it. It's not an easy question, okay? But you cannot give up. You have to do it.
Yeah, I knew I could start with a tough question to you, Shankar, so I took the liberty. So, but would you add something to that?
So, well, I can't say much about India. I don't know much about India, but I think the first thing to say is that we haven't defined what quantum science means. Quantum science, in some sense, started in 1900, or you could even say before that, experimentally, because we were measuring things that depend on quantum mechanics. Quantum science is not the same as quantum computing. Let me, first of all, emphasize that. Quantum computing may be of use, may not be of use, and it's certainly gotten a lot of hype, as you can say, but there's much, much more to quantum science than that. I mean, you could, in some sense, all of chemistry is quantum science, because quantum mechanics, the laws of quantum mechanics, govern how electrons behave in atoms and molecules, things that were not understood before 1900, before 1930, really. today, we maybe not necessarily consider all of chemistry quantum science, but it really is. When we talk about quantum science, we tend to mean things where quantum mechanics is playing kind of unexpected roles, things that we didn't understand before. And that includes quantum computing, of course, but it includes high-temperature superconductivity. It includes, well, superconductivity for sure is quantum science. Much of materials physics is quantum science. There may be quantum theory involved. There's certainly quantum-type experiments involved. There's a tremendous amount of work on low-temperature experiments. How do materials behave at low temperatures? How do they behave in strong magnetic fields? They could be two-dimensional materials or not. What are the kinds of different behaviors that materials can have that maybe could be exploited some way, maybe not. But we're trying to understand how electrons behave in materials, let's say, under weird conditions of nanoscale, very, very thin layers, very small devices, strong magnetic fields. All of this is quantum science, and there's a tremendous amount to be learned. I can't say how useful it will be. Nobody knows how useful it will be, but there's a tremendous amount to be learned, and from my point of view, it's very exciting. I mean, intellectually, it's just one of the most beautiful subjects that one could imagine. And I think, to be a quantum scientist, any kind of science can be exciting, and to do some research and maybe be the first person in the world to see something, maybe a small thing that hasn't been seen before, that's tremendously exciting. It's a great privilege to be able to do that. And even if you're not doing original work, to understand the beauty of quantum mechanics. And, it's not an easy subject. You have to study for years to get to the point where you have the mathematical skills to understand what's going on. A lot of people can look at a picture and say a beautiful picture, or you hear music. Quantum mechanics is not that way. To really understand it, you have to study it. But when you do, I think it gives a kind of thrill and excitement that you find you're one of a minority, not an infinitesimal minority, but one of a minority of people to understand how the world really works and how mathematics ties into physics. And I think those are the things that are important. I think they're important in India. They're important in everywhere.
Yeah. Okay, thank you very much. Do you have something to add, Klaus?
But also in our daily life, I have a microphone, everything in microelectronics is quantum science. And if you look at programs, then it's always quantum computer is one part, our quantum sensors to measure something. This is our real life already for many, many years in the past. We have just a new name for very sensitive sensors, and we can really see very small changes. And to collect information and data is one of the important things in modern devices, electronics, to collect informations and to smell, to measure something, to see something. This is modern quantum physics in semiconductor. And it's a political decision whether you invest in this field. You can decide to go to nuclear energy as a focus or to space experiments, but these are political decisions. And I think in semiconductor physics, nanoscience, quantum science, this is much broader applications than in other fields. And our daily life would be different if we had not the quantum physics. And if you use a laser or in optics, everything is quantum physics. And then we can treat now electrons like waves. We know from optics to see all these phenomena. This is really broadens the field. And if I have to decide with the potential of application, then quantum science and material physics is a fantastic field. Yeah.
Okay. Thank you all for this very nice and varied answers to my question. Now, the rest of the questions are question sent by very young people. So I'm going to start off as an experimentalist. I'm always curious about it. So maybe let me ask this question to Professor von Klitzing. So the question is, many breakthroughs seem accidental in hindsight. In your experience, how much of the discovery comes from preparation versus recognizing the importance of something others might dismiss?
So I published the data, the raw data, already 3 years before the official discovery, and everyone who could read literature had the chance to see it. But we were biased that Hall effect is a dirty effect. If you look at textbooks, there are so many corrections from scattering, from the geometry of the device. So everyone was happy to have 10% accuracy in Hall effect measurement. So we were biased against the dirty effect. And therefore I mentioned today that suddenly I saw that some years earlier, at the same position on my graphs, I see something reproducible, and must be some physics behind it. And to decide to look for this effect, which was not my goal in this experiment, and to give the freedom also, if you do experiment and you don't understand something, to continue in another direction. I think this is very important and the basis of basic research.
Okay, so serendipity has, and sort of following something unusual has its rewards.
Yes, and my recommendation to all experimental scientists, not ignore something which you don't like because you wrote a proposal, you want to see something, and it's not on your track. And normally we have 90% dirty effects in the experiment, and as a good scientist, you have to decide what is dirty effect. You need some explanation to identify the dirty effect from some interesting effect. And fortunately, as an experimentalist, we see the truth already. It's complicated. As a theoretician, you have some input parameter. You assume something. You never know whether this is the full truth in nature. And this is a nice thing as an experimentalist, but you need a feeling what is dirty effect and what is an interesting effect.
Okay, thank you. This is another question asked on the webpage where we had asked for possible questions. So let me address this question to Professor Halperin. Is there a concept in physics that still makes you think, in your wisdom, why is this problem so hard that after years of thinking about it, is there a problem that still stands out after years of thinking it's unsolved in your mind?
Well, I guess for me, it's rather there's so many problems that I don't understand. If you ask me, is there one single problem okay, I could say, what's dark matter or something like that. There are certainly problems that anyone can say, yo, this is crazy, but we don't understand it. I wouldn't put things in anything that I have any input. I have nothing to say about. I'm sorry, I can't make any useful input to what's dark matter. But within the field of quantum physics applied to condensed matter, to everyday, to matter on Earth, there are just lots of different things that I could mention some things from quantum Hall effect, where something called the 5 halves problem, where there's a state, a quantum Hall state with a quantum Hall conductance, 5 halves in von Klitzing's units, and there are different theories about what's going on, but the experiments don't agree with the theories, and I don't understand why. So this is, an example of a problem. Now, I think there is something fundamental there, but I don't know what it is. Mm-hmm. There are other things where there are experiments where I don't understand what's going on, and maybe it is just dirt. Maybe it is just we don't understand the material. So there's a range of things, and for me, at least at my stage, I'm very much interested in trying to understand experiments, trying to understand what goes wrong. Why I look for things where theory and experiment don't agree, and try to understand them. And most times the answer is not going to be terribly exciting. I'm not going to discover a quantum Hall effect that way necessarily, probably not, but that's what motivates me, and I think it's very important because that's the way you find new things, by trying to understand the old things.
Okay.
Okay, but what do you mean with understand? So quantum physics is the explanation of observed experiments, and I mentioned today that particle wave is one of the mystery, because we have no daily experience that electrons can have both the particle and the wave picture. And therefore, I mentioned the experiment where you see really this, and quantum physics is the best description of behavior of electrons, for example. So the theory, we don't know whether quantum physics is the last word to describe our universe, but it's the best description what we observe, yes? So it's helpful to understand what we can see in experiment.
I want to add something to what just Klaus said and what Bert said. So this question, rhetorical question, is quantum physics the ultimate description of the universe? I actually have a very strong opinion. It better not be. I find it very difficult to believe that 10,000 years from now, the Klaus von Klitzing 10,000 years from now will be sitting here and talk about quantum Hall effect with exactly the same quantum mechanics describing it. That will be so boring, and that will be historically unprecedented, that somehow in the 20th century we figured out everything. I know a lot of people feel that way, but I think it's just philosophically impossible. Okay? So of course there'll be something. But of course we don't know it today because we know things through data. Okay? I mean, everything we learn in science is an experimental thing. So on that, what Bert was saying, your question has two levels. One is that we can ask meta questions, which are almost philosophical, but they're physics questions, like what is dark matter? Even more mysterious, like dark energy. If you think about it, why is there a constant which is 0 up to 123 digits, and then it's 1, okay? But those are very meta questions, almost on the level of philosophy. In condensed matter, we stay away from things like that. We tend to ask concrete questions, which are important and often do not understand. So I'm going to give 3 examples, let's mention them. One is something I do not actively work on, high temperature superconductivity. It's not something people are actively working on because it's basically the burial ground of theoretical physicists. You come up with an idea and everybody should sit down. But there are many mysteries that I do not understand. For example, you do not understand why the TC is actually very low. It's not very high because most people think it's electron-electron interaction. The scale of electron-electron interaction in materials is 20,000 Kelvin. Why is the TC only 100 Kelvin? So there is a big mystery there, and we do not have the ultimate answer. Sure. And in quantum Hall context, I would like to know, Klaus didn't touch upon it, I know Bert has thought a lot about it, is to what extent is the purely age effect? Does the bulk play any role? And does the size of the sample matter? Okay, where is that correction coming? We know if you make it very narrow, you are not going to see the Klitzing constant. What determines that size? This is probably some details, but I like understanding details. That's my life. And on the third level, I'd be very much interested in knowing, Long Ju is sitting here, he saw in rhombohedral graphene a superconductivity. It's called chiral superconductivity, which has connection to this 5/2 and the quantum computing. I would like to know what's going on there. It's a very difficult thing. There are something like 50 theoretical papers, but I don't think we completely understand. So our questions are only concrete questions would make progress in our field.
Okay, thank you. Let me ask a question from here. I'm reading out the name. Some of the other places, the people said that don't read out our name, so I did not read out the name, but they were all not my questions, but some young students. So this is from Ashtana Dabushankar, who is in grade 12, maybe she's here, from the Lodha Genius cohort program. So her question is, many of the transformative technologies in history emerged from physics that once seemed completely abstract. So what do you think are the unanswered questions in quantum mechanics that are most likely to result in some revolution? So she's asking for some guidance of something which is not so well known now, will revolutionize our world.
Yes, room temperature superconductor was one of the questions, yes?
My response to that would be, If I knew what that is, I'll not be wasting my time sitting here. I'll be back in CMTC calculating away. We don't know answers to these questions. After the fact, it all looks clear, as Klaus explained very clearly. Klaus was trying to understand the insulating regime, whether it's missing electrons or the scattering time going to zero. That's what he was trying to understand. And he discovered an effect which was around. He saw it before. So it's very difficult to answer this question. After the fact, it becomes very clear. Why didn't we ask this question? So I really don't know the answer to this question. But
I don't have anything to add to that. One could speculate about maybe very sensitive detectors or sensors of one kind can be very important for in both in medical applications, maybe understanding things that are happening in the atmosphere. I think they're all kinds of applications of physics to other fields that we don't know yet, or we don't know what they can do.
Yeah, but I mentioned this memory of phase of an electron. I think this is something fascinating new direction in quantum physics.
Well, okay, so let me just say something about I think you could take different attitudes towards this. I don't think this is an application. Some people would say this is a philosophical question to understand how an electron can be both a wave and a particle. And I have a lot of sympathy for people who are trying to understand that question. But experiments are never going to shed more light on that than I think we already have. We've known this fact for since the 1920s. Everything that's predicted by quantum mechanics on Earth has proven to be right. The theory doesn't, it makes the assumption that this is true. I have no doubt that it's true at every scale that we can measure today. I would agree that it has to break down at energies at the Planck scale. There are places, it can't be the ultimate description of the universe, but it is pretty darn close to the ultimate description of everything that we can measure in the laboratory. And for me, that's enough of a challenge.
Okay, thank you. There's one question from Arjun Gadi, and he's asking some question about, I think, looks like a career advice. Young researchers are growing up in an era of rapidly advancing technologies and trying to contribute meaningfully. In your view, what does it really take for a young researcher to win a Nobel Prize today? So Arjun is ambitious, which is great. I don't know if Arjun is in the audience, but if you are, maybe you can identify yourself. I don't see, but maybe one of you has some...
I didn't understand the question. What is the question?
His question is, in your view, what does it take for a young researcher to pick up an interesting problem and make an impact?
Okay, I will try. I mean, the thing is that what is an interesting question is depends on one's perspective. What is interesting to me may not be interesting to somebody else. But I think for me, what it takes is just extreme passion in being curious about things and not worry about impact on those things. If you start worrying about impact before the work, I think you have lost the game. So what I would say the most important thing is incredible motivation and incredible passion for doing science. Yeah. And when I take students, that's the only thing I look into. Everything else is secondary.
Okay.
Yes, to be enthusiastic about science, you have to love it. And for us, it is a hobby. And we are lucky that we have a job and a hobby and have this international atmosphere. And I think everyone wanting to stay in fundamental science should have this international communication and to know his level in worldwide competition also, to be at international conference, to interact with other people, to be excited to see something new.
Okay. this is another question which says, what do you think matters more in becoming good in physics? Deep understanding or undying curiosity is the question.
I think we touched upon this in the last answer. They are connected. I mean, you cannot say, you have to love the subject enormously so that you're not worrying about these things, you're trying to figure something out to the end. You know, I will repeat what Klaus just said, you know. We are very lucky that we, you know, can make a pretty good living doing something we love. I mean, how many soccer players make a living out of soccer? The percentage is almost zero. So in some sense, we're very fortunate, and I think that curiosity is the only thing that matters. I mean, Bart may want to add something. You know, he has been doing physics for a long time.
No, I definitely agree. I don't think the right question really is to ask what to do to win the Nobel Prize.
Exactly.
Physics is not, it's not a soccer match. It's not a cricket match. You're not trying to beat everybody else to get what you're trying to, I think you could try, but I think that you're very unlikely, very, very, very unlikely to succeed that way. But if your goal is to do wonderful stuff and to learn and have the excitement of it, and if you're really smart and really lucky, you might win a Nobel Prize. That's nice, but that's not what you're working for. Shouldn't be.
Okay.
You can steal it, then you have no prize.
Okay, thank you. I think we can open up and take few questions from the audience. I would ask you to just raise your hands, and some volunteers will come to you, and only then please ask the question. And I request you to briefly ask the question rather than giving a monologue. So please get to the question quickly. So
Receive the mic.
maybe we can start from here. Please
Hello?
stand up in the back because of the light I cannot see very well. So if you're in the back, please stand up. Yeah. Yeah, please ask your question.
So, hello.
Give your name and ask the
My
question.
name is Suraj Kawale. It's a pleasure to meet you, Dr. Klitzing, and the panelists, of course, Dr. Jain as well. And I would like to ask a question that there has been recent research and development in quantum gravity. There has been the development of string theory, and there's not a lot of experimental progress in that direction. A lot of work is theoretical. And my question is, I would like to ask you whether how worth it is to pursuing that direction of physics.
His question is about how fruitful is that search in case of quantum gravity. Okay.
Well, the point is, none of us works on it, so we should be very careful. So you probably know as much about quantum gravity as I do, but of course it's a question that is of deep philosophical and intellectual interest, because as Bart emphasized, you know, combining quantum and gravity have been a very difficult question. Einstein tried to do it, but he ignored all the other interactions, and then he failed. So it's a very important question, all of us will agree. Okay, but whether somebody should work on it, you know, why are we here is also a very important question. Okay, why do we exist? Okay, the deep, important philosophical question. So whether you should work on it or that depends on how much you love that subject. Progress will be slow because it's a very old subject. So that nobody can advise you. I mean, this is my view, okay?
Okay, in the back, there's a girl student wearing the school uniform. Can you please stand up and ask the question? Yeah, please give the mic to her.
So I wanted to ask the question.
Can you please
on
state your name just for, yeah.
Aditi Sen. I'm from DPS. I came here after registering from my school. My main question was about the quantum Hall effect. I've noted down almost all my questions in my notebook, but since I can't ask all of them, I'll ask one. So in this effect, can it explain the states of a particle, for example, an electron? Like, can it describe the states of an electron, the data?
afraid I didn't understand the question
Her,
exactly.
I'm just repeating. She says, can measurement of the quantum Hall effect give information about the states of the particle?
Yes.
That's the question.
Yes.
Theory.
Maybe you could amplify what you mean by the state of the particle, because the word state has a very specific meaning in quantum mechanics. Is the wave function defines a state? Sure, we know. I mean, so maybe you have something more specialized in mind. I mean, the answer is yes. Okay, but perhaps that will not satisfy you.
Okay. Maybe you have another quick question. You can have a chance to ask the question.
Yeah. Can it affect the transformation? Like, can it explain the transformations between states? Because as we know that every particle has to obey conservation of energy, so it will always be in the lowest energy states, if I'm right. So can it explain the transformations between states? Like in one extreme there's another state, in another extreme there's another state, in the middle there's the constant state, the general state in which the particle is always in.
Well, I mean,
The end of maybe you can come and talk, and if you have a sketch or something, maybe you can try talking to them. I think these are interesting questions. Maybe come up to the stage at the end and see if you can convey some more clarity. Can you please stand up so that I can see you? Maybe you can, blue t-shirt. Yeah.
I think you need the microphone so that everybody.
Mic. Please state your name and then ask the question compactly. Yeah.
Hello. I'm Ameya Thakur, and my question was addressed to, in general, but specifically to Professor Shankar Das Sharma. So my question was, your research is based on many body systems, if I have to say broadly, and are there situations where numerical simulations initially suggest some kind of anomaly to standard physics, and when you're theorizing something, how do you distinguish it from something how do you distinguish it from a genuine emergent behavior from computational artifacts, like something that is a constraint of the system as compared to something that is actually an anomaly in the physics itself?
I think, did you want me to address it first? Is that what you said? Did you want me to address the question?
Actually, anyone would be great.
So what you're asking, let me rephrase the question, that in computer simulation you see many kinds of results. How do we figure out whether particularly interesting looking results is interesting or not? That's there is no standard recipe for it. This happens all the time. Students do simulation, we look at it, and it happens in experiment also. I mean, you should conduct an experiment, see something interesting, bam. Then you have to do a lot of work and look at it from all other possibilities. Are there obvious explanations or not? And it's open-ended. So you may conclude it's interesting. This has happened time and again in the subject that I spend most of my time on, called Majorana physics. In fact, I talked about it yesterday. And then you later on realize, no, what you thought is not quite correct, because there is a simpler explanation which we think about. And so there is no pattern answer to what you're asking. This is something one has to be very careful about. But this is not just a scientific theory. I mean, Klaus can comment on it. In experiment, you may see some signal, which may look fabulous, but it turns out that it has some very benign explanation. So this is what science is all about. This is what you do. Okay? It's hard work.
If I could add, I mean, with experience, you do develop intuition. It's not all logical, but you've seen many data if you're an experimentalist, and you kind of, this looks funny. This looks like it's just dirt. Now, the problem is, of course, you could be wrong in both ways. You can, so you want to sort of err on the side of saying this might be important. And then you have to say, well, what more experiments can I do to see if it's really important or not? But of course, you can't do this for everything. You still have to make some choices of ignoring stuff that looks like dirt, because if you don't ignore something, there's nothing left. So it's intuitive, and you're not going to get it right all the time either. But then hopefully one of your colleagues will get it right, because science is a cooperative effort, and you hope that, I think eventually the truth will come out.
Yeah, but this interaction between experiment and theory is extremely important. And I'm warning a little bit. Sometimes we have fantastic theories and a lot of experiments running to confirm a theory, and they ignore all other interpretation. So they sell their experiment as a confirmation of something. And you should think about an independent experiment from other way to confirm your assumption. And we have the possibilities to go from different angles to look at the problem and say, okay, if my idea is correct, then this independent experiment should give this result. So they have this control mechanism between theory, experiment. This is a fascinating world. And today, unfortunately, many publications are just looking for something to confirm, but ignoring all other interpretations. And but should be more careful not to publish only to confirm something exciting, and to have some confirmation from some other angle. If your assumption is correct, then you learn something for a next stage of experiment.
Okay, thanks. Yeah, can you ask the question? Can you get a mic?
My question was for Professor Dr. Klaus von Klitzing. Namaste, Dr. Klaus von Klitzing. My name is Shimon Ratan Khandekar, and I study in 8th standard, and I am from Lodha World School, Dombivli. I wanted to understand how does quantum research helps us understand the invisible world around us, and can we connect this to the nuances of pottery? And finally, is it sensible?
Who's it? So,
His question was, how does quantum science help see the invisible world around us?
what's the quantum science?
How does quantum science enable us to see the invisible world around us?
Quantum science is always explanation of the normally something outside our daily experience. But finally, quantum science is an explanation of some experiments, which is not our daily experience. And therefore I mentioned experiments where you have this duality between particle and wave. These are facts, experimental facts. Yes? So there are some observations which you are trying to understand. And the problem is that we have now sensors to see the atomic world, and therefore we have the macroscopic explanation, what we see originating from the macroscopic world. And this is the best explanation we have.
Okay, thank you. Can I have, maybe the person in the maroon shirt, can you get the mic?
Hello. Hello there, I am Viraj Kamani. I am a mechatronics engineer in the second year. And all these findings, I was just thinking as you were presenting, that it's good that you're finding stuff, but the true win of that finding is when it's applied practically. Like GPS without relativity would not exist. Modern tech wouldn't be as good without the quantum field effect. So maybe all these years we've been trying to look into physics, into quantum, and then after years it gets into tech, like we use it as proprietary modern consumerism tech. But what if it feeds in the reverse? Like, what if there is some tech that we don't know how to operate? We don't know how we can make it work, and then we go into the science of it. Like, I do want to make it work, like a problem-solving thing than a dart in the dark.
Can you just briefly get to your question, then we can address and give an opportunity to others to answer?
Yeah. This was my question. Like, how can rather than the physics feeding the tech, how can we have some unfounded tech or some tech that we don't understand, and we try using physics to get to know that?
Okay. Do you have any comments?
If we do not have any tech based on something we do not understand, that tech is not going to work. Okay? That's astrology and pseudoscience. So I do not quite understand what you're saying. By definition, there is no tech that works that we don't understand, because how that's not possible. So I think you have something very specific in mind, but it's probably not physics. For example, it's possible there is some herbal medication in some distant village in Borneo that works, and you do not quite understand why it works because nobody has worked on it. That's a different thing. So unless you can give a physics example, I at least don't understand what you're asking.
Yeah, okay. Maybe what we'll do is take another question. Thank you. Maybe one question, yes. Yeah, please.
I think you just mentioned that there is a lot of data which is there, which if you think differently, or as in your case, the same data was available for people, but they did not come to the same conclusion. With AI now coming up, do you think there is a role of all the data of all the experiments that has been done till now or for so many years to go back, put the raw data in, and then get maybe some new conclusions or some new patterns from all the experiments that you've been doing for so many years now?
Okay. Thank you for the question.
No, the acoustics so difficult here.
His question is will AI help looking at troves of data that we have and give something meaningful? Like, there is lots of unexplained experimental data which is published. Can AI go and look at and sift through that and say something meaningful? I think that's the question.
Data were nobody saw any significance of that. You realized
Yes, some kind of experience, and AI can collect much more data perhaps in the future to give you some hint in which direction you see something new. But this is a big question, how to identify the problems. But we have always more problems than solutions. And you should be aware, if you have some new knowledge, then you open new windows to see some consequences, to have new questions. And therefore you should not be angry to discuss some solution because you have to think that somebody will steal your ideas. There will be open some new questions. And so we will not end up that we have a solution for all questions. I compare this with the ball. The interface between inside and outside is our research area. We increase the size of this ball, and then the question, the interface increases, and therefore you will always ask questions. You can ask, what's the origin of life? This is still an open question. We don't understand anything about to answer these questions. So we have already in semiconductor physics enough complexity to enter then the biological area is the next step, and so there's so many open questions, and the education in solid-state physics is fantastic good basis to tackle other problems.
I use a lot of AI research, a lot. A transformer business, modern AI. My answer to your question at this point, if somebody does what you specifically ask, take a lot of data and ask AI, find something interesting, it will find millions of interesting things. Okay? It will just keep on feeding you interesting answers, except all of them will be wrong. Okay? So it will hallucinate, and you can force AI to give any answer you want. Anybody who has argued with chat, it will give you an answer. By the fifth round of the chat, you can force it to give exact opposite of what you originally said. So that is not the idea of surveillance. You have to have a pretty good idea, as Bart was saying, based on intuition, based on prior whole science, what it is that you're looking for. Then AI can be extremely effective. But if you just say open-ended question, here is the data, tell me something interesting, it will tell you something interesting, and you will be wrong.
Thank you. There is a question here. Maybe person in the back. Yeah, you. Please stand up and say your name and please briefly ask the question.
Okay.
No.
My name is Vijender, and my question to Klaus that like you have shown the PPT and reflected that we have defined units using fundamental constant. My question is that is we need to redefine the units again? And my second question is that how it is going to impact the general people, those who don't know about SI unit has been changed. So can you give me some example that they will relate it to real life, like the banner of this talk is from curiosity to real world impact. How this SI unit going to impact their general people who don't know about physics or something?
Okay, thank you. Yeah. So if you heard the question saying, is this changing of the SI, redefinition of the SI units that you said, is it going to change or impact common person?
He's challenging you, Klaus. He's saying does it matter? Defining things to this extent.
Okay. But, okay, there will be still new developments in the international system of units. I did mention it. We will have in 10 years' time a new definition of time, because we have much better clocks today, cold atoms and entanglement. So there's a lot of activities, even nuclear clocks are on the map now, but we don't know which one will be the best one. So we will have still a change in our international system of units, because the cesium clock we are using today works very well, but we have better clocks. And this is the only one which will change in the future. But all the other ones, to my opinion, these constants will never change. So even in 1,000 years, I hope that the Klitzing constant has the same value.
Great, thanks. Yeah, maybe one, maybe we have time for maybe at most one question, or maybe person in the back, black.
Hello?
Yeah, speak loudly.
So I'm a marketer and I've recently entered investment space. So my question will also be as such. If you had to put money into a commercial expression of quantum science, where would you do so? Maybe if not today's quantum science, what do you think is the next big thing? Because as we saw the article, we say that quantum computing is not really what we should be looking at, but there's a lot of money flowing into it.
I think our answers may be different. Each of us should answer it, because it's about money.
Her question.
I can start, because the point is that if I give you an honest answer, that if I want to make money from quantum science, where would I put my money? I know precisely where I put my money. I'll short all the quantum computing companies. But I have done it, it's taking long, but eventually I'll come out of it. But that is, of course, not the answer you're looking for. What will go into an application is a very difficult thing to answer. I'll give you one example. The thing that Klaus talked about, MOS, which is the heart of all modern technology, metal oxide semiconductor, it's basically a capacitor. The original patent for it was in 1926 by a guy named Lilienfeld in the United States. He precisely knew. He said, look, it's basically vacuum, it's a three-terminal device. And he proposed here the elaborate patent, proposed metal by electric field, bring the electrons close to the surface. There is another terminal to control this three-terminal device. And you can, it's going to revolutionize everything. But what he didn't realize is that you have to be Henry Schwann to make that actually work. Because the electric field that vaporize everything is not going to work with metal number of electrons. Then in 1936, a German professor, maybe by the name of Weber, wrote down the precise patent for MOSFET that exists today. There is no patent on MOS, because his patent was so good that it is exactly what it is. Everybody started working on silicon, trying to make a MOS. It didn't work. You know why? Because people didn't know what the surface is. People did not know that electrons are coming, but they're all getting eaten up in surface, so there was no effect at all. And Pauli made the famous statement that, semiconductors may not even exist. So science proceeds this way. There are things you do not know, unknown unknowns, that may prevent you from getting something. And then when the material science improved, then early 60s, what was realized was exactly the original idea of Lilienfeld, except not in a metal. So one has to be very careful predicting what will go into application. So I do not quite know. So, so after this long answer, I give up. I don't have an answer to your question.
Yeah, do you have anything more to add to that, or?
Okay, today they want to improve MOSFETs to reduce energy consumption. This is the main problem today. And today, neuromorphic or some other techniques, phase transitions, or other physical phenomena may be used in the future to be more effective. And the energy consumption is one of the problems today, yes. But there's so many new ideas, and if you're enthusiastic, you can contribute to this, yes?
Okay. But do you have anything more to add to this discourse? Okay. All right, I think we are out of time. I thank everyone for the interesting questions and for participating, and I thank particularly the distinguished panelists for answering some questions that were submitted to us. Thank you. So let me invite, right at the end, let me invite Ms. Deepshika Surendan from the Lodha Foundation to say a few things to end this very exciting discussion and public lecture. So over to you.
Okay. What a truly special evening this has been. I can see a lot of you walking out after getting your fill on what promises to be a very, very, very enriching experience for most of you. Before we bring it to a close, I want to take a moment to say thank you. Because evenings like these are only possible when extraordinary minds, institutions, and communities come together in the spirit of curiosity. To our guest of honor, Nobel laureate Professor von Klitzing, thank you for an inspiring and deeply thought-provoking lecture. I personally take away the fact that science can be the unifying force in this universe. You reminded us that quantum research is not only about understanding the invisible forces shaping our world, but about daring to ask questions whose answers may transform our future. Our sincere thanks to our distinguished panelists, Professor Alpern, Professor Das Sharma, and Professor Deshmukh, for enriching this conversation with their insights and perspectives, and for graciously and patiently responding to a stream of questions from a very engrossed audience. You will be, it's interesting, I hope, for you to know that we have 800 plus in the audience today, and a lot more who have joined us virtually on YouTube. A very special thank you to our partners, the Tata Institute of Fundamental Research. Few institutions have shaped India's scientific imagination as profoundly as TIFR. And as the Lodha Foundation prepares to launch the Lodha Theoretical Physics Institute tomorrow, we could not have asked for a more meaningful beginning to this journey. Thank you for your trust, your partnership, and your very generous support. A special mention to the Dean, Professor Ghosh, PRO, Mr. Iyer, Uzma, and others who have worked behind the scenes to make this evening possible. And to all of you in the audience, thank you for showing up with curiosity and openness. You turned a lecture into a shared moment of learning. Tonight, we leave a little more curious, a little more hopeful, and certainly more inspired, with a deeper appreciation of why research, even when it's difficult, it's abstract, it's invisible, matters so profoundly to the future we build together. On behalf of the Lodha Foundation, thank you for being here.